quantum algorithms for approximating partition functions.
Thank you, Sandy, and thanks to the organizer. So this talk will be in touch to what Anthony spoke about this morning. I will try to go one step further by looking at some application of Gibbs sampling, but also one step back by looking at classical instead of quantum Hamiltonian. So let me recall you what is the framework behind Gibbs sampling. So you are given a classical Hamiltonian, an inverse temperature, and the partition function at the corresponding temperature is defined as the trace of e to the minus beta h. So if you recall the definition that Anthony gave this morning of a Gibbs state, this was exactly this quantity. And you can connect the Gibbs state to the partition function in a very simple way because, as you can see, the partition function is a summation over all the probability that characterize the Gibbs state. And in fact, the partition function is just the normalization factor in the definition of the Gibbs distribution. So, as I said, the Hamiltonian will be classical, meaning that we can do an important simplification, which is that the energy basis of the Gibbs state is the standard basis. So it will help having much simpler algorithm. And we'll see that we can do much more quantum algorithmic technique on those type of Hamiltonians. Okay, so why do we care about computing partition function? Why do we hope that quantum computers may help in doing this task? Well, the reason is, as you know, one of the advantage of quantum computing is that it provides a way of doing faster statistical estimation for a lot of different tasks. So this is, for instance, the goal of quantum metrology. You have the so-called Heisenberg versus short noise limit. And there are a lot of quantum algorithms that helps you improve the performance of statistical estimation tasks, such as quantum phase estimation, quantum counting, quantum mean estimation, etc. So the goal that I would like to explain to you in this talk is try to give some answer to the following question, which is how far can we push the advantage of quantum computing for performing statistical estimation? So for instance, can we find very generic methods to turn classical statistical estimation algorithm into quantum one? Can we always achieve at least quadratic speedups? And can we also apply those kind of algorithm to highly structured estimation tasks, such as the computation of partition function? Okay, so partition function is a particularly interesting case because it is kind of very ubiquitous in TCS and in physics. This is a very important object in statistical physics when you want to understand the dynamic of a system, but also in combinatorics, where it can be related to the counting of certain graph structures, such as matching, independent sets, colorings. In linear algebra, where you can relate it to the computation of certain permanence. In convex geometry, with the computation of the volume of convex body or polytopes. In machine learning, etc. There are a lot of possible applications if you can compute efficiently partition functions.
Like in physics, you never really care about the partition function itself, but rather like by observables, the observables that you can. So dividing an expectation by the partition function.
But you mean like on top of the partition function, or?
Well, you're interested in what is the expectation of the other. For this, you don't need to know the partition function.
Yeah, but you care about the limit. This
is, I think, a different task, right? Like, of course, you could estimate the partition function by picking the right observable.
No.
But it's not going to be efficient.
No, because you always have to divide by the probability distribution. So you calculate an expectation value and you normalize your partition function to 1.
So you mean like you're talking about estimating expectation values on the Gibbs state?
Yes.
Yeah, but I think this is like a different task. Like I'm talking about really estimating this normalization factor.
Yeah, I think in physics what you care about is how this normalization changes as you change parameters in the system. Right? Mobilization itself is completely meaningless, right? You add 5 to your Hamiltonian.
No, that's meaningless. I mean, for those applications tells you that this is
In physics.
okay.
Physics is
Okay, in physics,
meaningful is how it depends on the parameters.
okay, but depending on the value of beta, you do get information about like the high temperature regions, I mean cold temperature and so on. So I'm not completely sure it's always useless.
If you add a constant to your energy, the partition function will change, right? And you have to change nothing about the physics. It's clear that the number itself has nothing to say about physics. So it changes when you change the parameters.
Sorry, just to clarify, are you saying that you need to know the partition function when you're computing? No. But you're saying you need to understand how it to compute it to understand how it varies with different parameters, and then that gives you insight into the physical system.
No, but it's more than that. It's you always divide by you kind of calculate the expectation value of an observable with respect to the probability distribution that is basically given by your Partition distribution, and therefore the absolute value of your probability that the norm of your probability is relevant. You divide it out. It's numerator and denominator. Indeed, if you do metronomic sampling, this does not allow you to calculate the partition function at all, but you can still calculate expectation values.
If you can calculate it, you could calculate some derivative using that. I want to.
But it's also not derivatives of the partition function, it's derivatives of observables.
No, it's derivatives of a logarithm of the partition function, which automatically gives you C prime over C, right? So you automatically get this normalized
But I think the main point here is that in combinatorics, statistical, partition functions play a very important role.
Yeah, but that's different. That's in counting problems you mean.
Yeah, without any problem. And this is your goal, right?
This is one of the possible applications. I mean, what we spoke about is like for partition function in general, but one such application is combinatorial. And I will actually develop an example which is related to combinatorics later on. Okay, so as I said, this is related to counting tasks and also to phase transition, because usually when phase transition happens, this is reflected into the complexity of computing the partition function. So unfortunately, computing partition function exactly is usually sharply hard, meaning you don't even expect to have an efficient quantum algorithm. But on the other hand, if you relax the assumption, meaning you just ask for a sufficiently good approximation of the partition function, then we do know of a bunch of efficient algorithms. So one such example is the Markov chain Monte Carlo method, which this talk is going to be about. But you also have Taylor's approximation, correlation decay, etc. So this is the main result that I would like to talk you about, which is a very generic quantum speedup that you can apply whenever you have a classical MCMC method for computing partition function. So the classical MCMC method is one of the most studied methods for computing classical partition function. It has been formalized in a very beautiful paper by Stefan Kovic, Vampala, and Vigoda, and others. And what you can do is you can turn this classical method into a quantum algorithm whose running time is a product of two quantities. On one hand, you have something that depends on the log of the number of configuration of your Hamiltonian. And on the other hand, you have a quadratic speedup over the running time of the classical MCMC algorithm. So this classical running time usually is also at least log of the size of omega, meaning that at the end, what you get is really a kind of a sublinear quantum algorithm with respect to this parameter. And the size of omega is exponential usually, so at the end, it's really all about polynomial speedups. So this class of MCMC methods include the best known algorithm for quite a lot of classical partition functions, such as in combinatorics, counting the number of independent sets, colorings, matchings, but also the related statistical models, such as the Ising, Potts, monomer-dimer models. And you can also kind of adapt this result to handle the computation of the volume of convex bodies and the permanent of non-negative matrices. It's kind of quite a general framework. Yes?
So what is related to work of Szegedi? Because he also showed some quadratics.
Yeah, it's going to be related to Szegedi's result. Yeah. I will touch on it in a minute. So I think what is really nice about this result, I mean, behind the speedup is the techniques which has been developed to arrive at this complexity, because this is a topic which has been studied over more than 20 years, and that help identifying interesting quantum algorithmic primitives. So this is a timeline, maybe omitting some papers, but those are the most some of the most important contribution in achieving this complexity. So it started at least with a work by Aronoff and Tashma in 2003. And as you can see, there has been in each of those works a slight improvement to arrive at this complexity. And each time it was with the introduction of kind of new quantum algorithmic primitives. So those results in red correspond to results on the quantization of random walk, such as quantum simulated annealing and Szegedi's quantum walk. In blue, you have the development of quantum algorithm for estimating expectation values with certain properties, such as an efficient way of reducing the variance of an estimator, how to make it unbiased, non-destructive. And in green, you have a different type of contribution, which I won't talk a lot in this talk, which is about computing cooling schedule. And this is again related to simulated annealing techniques. So I will try to guide you through this framework, giving you some of the main ideas, and in particular, what has been the last development that helped reaching such a complexity. And just to say one word about quantum Hamiltonian, I would say it is quite likely that a similar framework could be designed for quantum Hamiltonian. And in some sense, you may think about like what would be the right analog when the Hamiltonian is pretty quantum. And I think it is something that should be doable, at least if you only care about like polynomial time reduction between mixing and estimating the partition function. Okay, so to illustrate this framework, I will focus on a particular partition function for which I will describe the algorithm. And this is the independent set partition function, which is important in combinatorics. So this is how it is defined. As input, you have a graph, and you care about the independent sets of the graph, which means subsets of non-adjacent vertices, which are called occupied vertices. Okay, this is called the hardcore gas model in statistical physics. The goal would be to understand what are the statistics about the number of independent sets in a given graph. Okay, so in this particular example, this number is equal to 7. And usually this is an exponentially big number in terms of the number of vertices. So if you want to be efficient, you'll have to find something running in time polynomial in the quantity that you try to estimate. Okay, so as I said before, when you try to count something exactly, this is usually complicated to do. And indeed, for independent sets, if you ask for the exact number of independent sets, this is going to be sharply hard, even in very simple cases, such as bipartite graphs. So we will relax the assumption by looking at approximate counting. And for that, the problem is defined as follows. So as input, you receive the description of a graph G and a precision parameter epsilon, which is a real number between 0 and 1. And as output, you want to come up with an estimate S, which is equal to the number of independent sets up to a relative error epsilon. So this is the best known complexity, both classically and quantumly, assuming the maximum vertex degree in the graph is at most 5. So classically, you can achieve a quadratic running time with respect to the number of vertices. And quantumly, you have this speed up by applying the framework that I told you about. When the maximum vertex degree is above 5, you again observe some phase transition, and the problem becomes complicated again unless some complexity classes collapse. So for the rest of the talk, I will first try to give you some insight about this classical MCMC method for achieving this quadratic running time. And then we'll see how it can be improved to arrive at the quantum speedup. Yes.
So on the previous slide, you gave this definition of approximations. You're kind of get a multiplicative approximate of this partition function.
Right.
Maybe this addresses like Norbert's question from earlier. Like you're saying you want to compute, in physics you care about computing the derivatives of the log of the partition function. So here would be you would get additive estimates of the log of the partition function to arbitrarily good accuracy.
Yeah, you mean relative converting to additive if you take the log.
Right, so then you would be able to compute derivatives once you add it.
Okay, so this is, again, the partition function. So in case of independent set, I just change the parameter because this is like the most common parameter in that case. So instead of beta, this is denoted by lambda, the fugacity. You should just think of it as a temperature parameter. And the partition function can be seen as a kind of a weighted version of the counting problem of independent sets. So essentially, for each independent set, you have a weight, which is lambda to the power of the size of the independent set. So the larger independent set have a larger weight, and the partition function is a summation over all the individual weights. So depending on the value of lambda, the problem of computing the partition function may be easy or complicated. So when lambda is equal to 0, this is always equal to 1. So all the weight is on the empty independent set. And when you increase lambda, you put a larger weight on the largest independent set, so the problem becomes harder and harder. At some point, it will again become intractable. And the hope is that when lambda is not too big, so let's say lambda equal 1, then if you can compute Z1, you would exactly recover the number of independent sets. Okay, so we'll try to use this idea of like slightly increasing lambda to come up at this estimate. So what is the very general idea of this MCMC algorithm? The idea is to use a connection, a very deep connection, which has been studied a lot in TCS, between the ability to sample the distribution and the ability to estimate related statistics. So in the case of the partition function, there is a very natural distribution. This is the Gibbs distribution, of course, which is this distribution proportional to the weight of the independent set. And what can you do if you know how to sample from the Gibbs distribution? Well, you can do the following thing. You can estimate the ratio of the partition function at two different parameters. To see why it is the case, this is a simple exercise. If you take the expectation under the Gibbs distribution at value lambda, and you evaluate the following quantity, which is lambda prime over lambda to the power of the size of the set you just sampled, then in expectation, you will indeed recover the value of the ratio. So it's not yet the partition function itself, it's a ratio, but it's quite close to what we want to do. And this estimator is unbiased, meaning if you take many samples, you may hope to converge to the true estimate. Okay, so let me decompose each of those two tasks to see how we can arrive at the final algorithm. So first, for Gibbs sampling, the usual approach, which has been developed this morning by Anthony, is to run a Markov chain whose stationary distribution is exactly equal to the Gibbs distribution. Okay, so in case of independent set, you can run a very simple Markov chain that just apply local updates. So essentially, you choose a vertex uniformly at random, and you make it occupied with a certain probability as long as the set remains independent. So this is called the Glauber dynamics. This is a random walk over the graph of all configuration, and you just do local updates. So it's quite easy to prove that it does converge to the right distribution, the Gibbs distribution. What is much more complicated to show is that the mixing time is not too large. And this is essentially what is known for the Glauber dynamics. I mean, this is a result that that was shown in full generality quite recently in a breakthrough result by Shen Liu and Vigoda. And they show that the mixing time of the Glauber dynamics for independent sets is going to be n log n. So it's very small. It's essentially the best you can hope for.
And you mean if it's already in there?
You mean for the second step?
So in some places you decrease the size of the independent set.
Yeah.
If the vertex you choose wasn't the independent set, then you throw it out.
Yes, so here you can decrease the size. Like if you pick the great vertex, you have a certain probability of decreasing the energy. Okay, so we know how to sample efficiently from the Gibbs distribution classically.
For all numbers?
No, so for lambda, like in the feasible region, like for independent set, it would be like if the maximum degree is 5, it would be up to lambda equal 1. Okay, 5 is because when lambda is equal to 5, you have this result. Like, so when lambda is larger than 5, there is no efficient algorithm for computing the partition function at value 1.
Before the physical.
I mean, this is like before the phase transition happening. If you care about another value of lambda, the maximum degree at which you observe the phase transition may will be different. It's like there is a trade-off between which partition function you want to evaluate and when is the phase transition happening. Okay, so how to estimate the partition function? So the idea is to go back to this graph and observe that there is an exponential gap between what is easy to compute, the partition function at value 0, and what we care about. So what can we do is some very natural idea, which is to try to slowly move from an estimate of Z0, actually from the exact value of Z0, to an estimate of Z1. So this is based on like using simulated annealing approach. And this is how it is done in practice. So what you do is you pick a sequence of intermediate fugacities that kind of interpolate between the easy case and the case that you are interested in. And you can express the partition function at value 1 as a telescoping product of consecutive ratio of partition function. Okay, and each of those ratios, you can estimate it independently by using those random variables. So of course, there will be a trade-off between two different things. The first one is if the schedule, meaning if the number of intermediate value is extremely important, then you may hope the partition function to change very slowly, meaning you will need very few samples to evaluate each ratio. So in some sense, you want to balance the length of the sequence with the variance of the estimators to make the estimation as efficient as possible. And what can be shown is that there do exist such a very efficient way of balancing those two requirements. And essentially, at the end, in total, you will need about order n Gibbs sample. Yes.
So do you have a proof that there's no phase transition between lambda between 0 and 1?
When the maximum degree is 1, is 5.
Yes.
Because
we're kind of assuming this wrong, you know, that
I mean, at least algorithmically, we don't have a phase transition. Like this is of the same complexity in the entire regime. So when number is between 0 and 1, we have like n log n mixing time. And then above maximum degree 5, I mean, what do you mean? Okay, say again, I'm not sure to understand the question.
basically you're taking derivatives there of your partition function. Oh, and then there's a phase transition.
There is no phase
lambda
transition.
between 0 and 1, that would diverge.
No, there is
And
no
so
phase
the
transition
question
between
is there a
0.
proof that there's no phase transition? Independent for the graph. So it could be that for some graphs there is actually a phase transition.
Okay, so here when I'm saying phase transition is more like in terms of complexity. So in the entire regime, you don't observe a change in complexity for something from the Gibbs distribution.
If that's actual, right? Probably. which relates to the question how quickly the distribution changes.
Yeah, so it does not change.
That's
Yeah. So it does not change much. Like there exists a short sequence of values that will guarantee that each has a very small variance. Each estimator has a bounded variance. A small what?
not so important that the value is small, but it converges small.
Yeah. So I'm saying like a small variance, which tells you that you can just pick a small number of samples and you will arrive at a good estimate. So overall, you will need just order n Gibbs samples. Each Gibbs sample costs you order n log n. So this is how you reach the quadratic running time for estimating the partition function classically. Okay, so if there is no other question on the classical method, let's move to the quantum one. So how can we speed up this this classical MCMC algorithm?
Sorry, can I ask just to clarify? Yes? So for this max independent set is MP hard. So in some limit, I guess this problem becomes the independent set.
Yes. Yeah.
Which parameter is it that scaling in the limit would give you that, and the complexity should blow up exponentially? This algorithm. It must be that the mixing time at some point does go through some phase transition and becomes.
Yeah, and you ask what do we know about the mixing time in this equation?
I mean, I think this relates to what Frank and Norbert were saying. Doesn't this go through a phase transition because this mixing time must blow up to the exponential limit?
It does blow up.
And in which parameter? Maybe I just missed it.
Well,
Okay.
In lambda, like the temperature.
You said earlier that at the phase transition, it becomes more difficult to compute the conditions. Why is that?
I mean, above the phase transition. So that is like a cutoff value. When you are above this value, computing the partition function depends like sharply hard, NP hard.
You mean in the place where you have more than a single Gibbs state?
No, you do have a single Gibbs state.
So it becomes harder at high temperatures?
It becomes harder when you increase the value of beta, the inverse temperature. So for the small temperature resolution. So yeah. Only talking about like the regime in which you can hope to have efficient point time. So for the quantization, there are essentially two branches of work which has been developed to arrive at quantum speedup, and are related to each other. So the first one is, how can we convert a classical reversible Markov chain, such as a Glauber dynamics, into some types of quantum works that have some nice properties? And the second branch of work is, how can we estimate expectation values on the one eigenvector of those quantum works? So those are like unitary operators. And as you'll see, this one eigenvector is actually encoding information about the Gibbs state. So let me start with the first one. This is Szegedyi's quantum work. But okay, a first attempt would be to say, what if we try to just speed up the task of sampling from the Gibbs distribution? Okay, so we can do it in n log n classically. What if we try to do it faster in the quantum setting? So this is something that usually we don't know how to do. I mean, there is no clear answer to this question. And it's quite unlikely because, I mean, you are working over a Markov chain of diameter n, so it's not really clear how you could get like a sublinear running time. So instead, we will do something else, which is a different task, but which is more of a quantum type. What we can do is we can simulate in time square root of the mixing time, the reflection, so it's a unitary operation, through the quantum encoding of the Gibbs state. Okay, so this Gibbs state, if you were able to prepare it, you could just measure it to get a classical sample. This is something we don't know how to do efficiently, but we know how to implement the reflection through this quantum Gibbs state. So in some sense, the way you should think about this result is that classically the natural resource, the natural sampling resource, is to draw an element from the Gibbs distribution, which you can do it in time n log n using the Glauber dynamics. And when you move to the quantum setting, the natural equivalent is not to draw a sample, but it's instead to implement these reflections through the quantum Gibbs state. And for that, you do get a quadratic improvement over the mixing time. Of course, there is a question of what can you do with such a reflection. But at least, we have identified a task that can be done more efficiently. Okay, so just a quick description of how it can be achieved. This is the so-called Szegedi quantum walk. This is a very general technique that can be used to turn any classical reversible ergodic Markov chain into a quantum unitary operator whose one eigenvector is encoding the corresponding stationary distribution. Again, what's important in this conversion is that you can relate the eigenspectrum of the initial transition matrix to the eigenspectrum of the unitary operator. And essentially, if you have a spectral gap which is 1 over n for the classical random walk, you will get an eigenphase gap which is 1 over square root n for the quantum unitary. Okay, and then you can just run quantum phase estimation on this quantum walk operator, and it gives you a way for simulating these reflections through the quantum Gibbs state. Okay, so now let's move to the next step, which is how can we use this type of unitary operation? And the goal is to estimate expectation values on the quantum Gibbs state. So for instance, if we go back to this ratio of partition function, you can estimate, rephrase this ratio as the following quantities, which is exactly the expectation values I showed you a few slides before. Okay, so this is where I will try to guide you through this quantum algorithm for estimating partition function, this framework which has been developed. And as you will see, there are several steps. In some sense, it looks like to the classical approach, but there are some differences, some changes, which are due to the fact that we only know how to implement this reflection efficiently. Okay, so a first attempt would be to do the following thing. So let's try to do the same as what we did in the classical MCMC method, meaning what we could try to do is to estimate each ratio separately in order to compute the telescoping product. And we could try to do that by just using the ability to reflect through the quantum Gibbs state. And the goal would be to come up with a quantum expectation estimation task that can do that efficiently. So unfortunately, we don't know how to do that efficiently. In order to make the problem easier, we'll have to make one more assumption, which is that as input to this quantum expectation estimation, we are given a warm start, which will be one copy of the corresponding quantum Gibbs state, and just a single copy. So in some sense, you should think of this copy as pointing you in the right direction to start the quantum expectation estimation. So of course, the question is, where does this copy come from? Because, as I said, this is usually complicated to prepare. And to obtain this copy, we will adapt the framework a little bit. So we will assume that at the end of the expectation estimation, by some magic, we are able to restore the copy that we are given as input. Okay, so for the first value of lambda, this is very simple because the first quantum Gibbs state is trivial. It's just the empty independent set. So we can just create it from scratch. But when lambda increases, you cannot just create a new quantum Gibbs state from scratch. It would be too expensive. So how can you, why this ability of restoring a copy of the Gibbs state is useful? Well, if you know how to do that, you can do the following thing. you can apply quantum annealing to slowly change one gate state to the next one just by using a few applications of the corresponding reflection operation. Okay, so if I zoom in this quantum annealing, essentially what you do is, because consecutive quantum gate states are very close to each other, you can just apply, let's say, fixed point amplitude amplification. It just requires to use the reflection operation, and you can change one gate state to the next one in very, very quickly. Yes?
So do you need the Gibbs state, or do you just need the sample with the right probability?
No, you really need the quantum gate state. The full, yeah, the full gate state. And you need it like without garbage, like a coherent encoding of the quantum gate state. Because this fixed point amplification, really requires to have like the quantum encoding of the state. Okay, so this leaves the question of how to come up with the quantum expectation estimation task. This is the only remaining piece in the framework. And those are the requirements that we would like to achieve. So as input, you are given, okay, so here I will focus on a simplified case in which we just want to estimate the expectation value of a projection under the gate state. Okay, so I'm just picking the simplest observable that you may imagine. It can be generalized later on to an arbitrary observable, but I will just show you the base case. So what's the goal? So as input, you are given the description of the projector. You are given a single copy of the quantum gate state, and you can access this reflection a certain number of times, t, which morally correspond to the sample complexity. Okay, classically, it will be the number of classical gate sample. Quantumly, this is the number of reflection you applied. What the goal? As output, you would like that the first register still contain a copy of the quantum gate state. So in some sense, you haven't destroyed the quantum gate state. And also, you want a good estimate of the expectation value, meaning that ideally, you would like to have an unbiased estimate with a low variance in order to achieve the right concentration inequalities when you take a product of estimates. Okay, so this type of subroutine is actually useful in many other applications. It has also been studied for other applications of the Monte Carlo method. So it's a very general algorithm. And it's quite simple to achieve if you combine the right tools together. So let me show you how it works. The idea is to start with the Grover operator, or a variant of the Grover operator, which is defined as follows. So first, you apply a reflection through the observable, which is a projector. And then you apply a reflection through the quantum gate state. Okay, so it costs you one resource of applying this unitary. And what you can show is that the quantum Gibbs state is a superposition over eigenvectors of this operator, whose eigenvalue is encoding the right expectation value that you want to compute. So when you have an operator encoding something in the eigenphase, what you want to do is you want to apply phase estimation. So this is what it would mean in this case. So as input, you have your quantum state, which is not an eigenvector. It's a superposition over eigenvectors. It's important. Then you apply a sequence of iteration of this Grover operator, and then QFT and measurement. So when you do the analysis of this algorithm, you can prove that it does give you quite a good estimate of the expectation values. However, it has two drawbacks. So first, in general, what you get in the first register is not exactly the quantum Gibbs state. And actually, in some situation, you can get something orthogonal to the quantum Gibbs state. I mean, how far this is to the original state depends actually on the expectation value. The second issue is that this estimate in general is not exactly unbiased. So there is some bias in expectation. And this bias, when you take a product, when you take the telescoping product, it will accumulate and it will kind of destroy a little bit the quantum advantage that you may hope to obtain over the classical estimator. So how can you fix those two issues? The idea is to study a kind of a new variant of phase estimation that gives you much nicer guarantee on the output. But let me explain you what this new phase estimation primitive is doing. So again, you will start from the quantum Gibbs state, but first you will sample uniformly at random a phase shift that you will apply on this state before starting the quantum phase estimation. Okay, then you do phase estimation as before, but instead of measuring the output, you copy it to a new set of registers, and then you undo phase estimation, and you measure both the new qubits and also the old qubit that were used by phase estimation. And finally, at the end, you apply some phase correction that kind of subtract the original phase shift from the estimate. So the first nice property of this new primitive is that this random phase will kind of help you to obtain a much smoother distribution on the output of phase estimation. It will give you a distribution which is fully symmetric around the phase estimate. And the second important property is that this trick of putting the result into a new register, which is related to uncomputation or rewinding, you can prove the following thing. If you post-select on observing the all zero vectors in the register of the phase estimation, then condition on that, you will exactly restore the right value of the quantum Gibbs state. So this post-selection, there are two important things. The first one, it has to succeed with high probability. I mean, this is something that you can show. And secondly, this post-selection will modify the distribution, the output distribution for the phase estimate. But if you make the calculation, you can prove that this disturbance is not too important. And this is essentially a picture of what you can prove at the end on the outcome distribution of this new quantum phase estimation primitive.
Why do you need the smoothing with the random phase for the estimator to be unbiased? Or?
Yeah, for the estimator to be unbiased.
Sorry, the probability for post selection, is it over how many? Like
it's a constant.
You have to amplify it then?
So you can amplify if you want to succeed with like overwhelming probability, but it's a constant.
So it's a random phase shift. How do you do this? This is like for every qubit a random shift, or?
No, it's like a global shift. So yeah, for every qubit you apply.
But I don't understand. A global shift, a global phase to a wave function doesn't do anything. No?
It does, but I mean, you do it before and after doing the phase estimation, so it will change the output estimate.
So by a phase shift, do you mean apply a phase gate rather than just a global phase? Zero rotation? Or is it like control on something?
Yeah, it's a control phase shift. So like you have a register holding like a distribution over the theta, and control on this register you apply the phase shift.
I guess you're actually implementing this into U, right? Otherwise,
Okay, maybe I'm wrong in the picture.
So you keep it on the register with description of theta? Is it what you said?
This is maybe
You probably implemented that distribution.
Yeah, it's in EU. Because we want to globally change the eigenphase. So yeah, I think I'm wrong in the pictures.
Otherwise,
Otherwise,
the
it
phase
makes
will not
no
be
sense
shifted
otherwise.
by
Yeah, yeah.
Right, you're shifting the phase by tipping.
Yeah, yeah, you shift the phase each time you. Okay, sorry for my
So is there a phase in the eigenvectors?
What does it mean to say again?
When you go back, you have the eigenvectors of complex time. Just relative phase that it changes.
Yeah, in general, if you do standard phase estimation, the relative phase between the eigenvectors over which pi is supported will change. Like pi is a superposition over two eigenvectors of U. And when you do standard phase estimation, the relative phase between those two eigenvectors is going to change. So this is why the states can be kind of destroyed in the process. And to handle that, we use this uncomputation trick. Okay, but this random phase shift is for something else. It's for making the outcome distribution symmetric. There are two different requirements.
Yeah, so where is the random phase? I didn't catch your answer to the question.
So random phase shift is applied on the unitary U. But to really find U, you cannot symmetrize over all the random phase. If you don't do that, you still get a good estimate, but it's not the distribution is not symmetric.
So it's like you replace U with e to the I theta times U in this picture everywhere. That are oh.
Yes. So this is yes.
Sorry, maybe I'm missing something. You make such a big deal of not destroying pi, the state, but to implement a U, presumably you basically have to prepare that state in some way. So why not just prepare a new copy?
Why do you need to prepare the state?
It's like two projection onto pi minus identity, right? How do you implement that without having some kind of subroutine to prepare pi, the state?
No, so this is what I said. So we don't know how to prepare the state efficiently, but we do know how to implement the reflection.
Okay, maybe.
This is the whole point of this ZD types quantum work.
Okay, sorry, maybe I missed that. Okay.
But yeah, those two tasks are of a different complexity. Like if you know how to prepare, you can implement the reflection, but the other way around it is not cool. In some sense, this is like a simpler task than preparing the state.
So I guess the reason you can implement the reflection operator is because pi is the stationary distribution.
It is the you can only prepare the reflection for the stationary distribution of the random walk. Okay, so this is just a picture showing the outcome distribution after T steps of three different type of estimators. So in red, you have classical empirical mean when you just collect a bunch of classical Gibbs sample and compute the average. So it is an unbiased estimator, but the variance is pretty large. It's 1 over square root of the number of classical Gibbs sample. In green, you have standard phase estimation that does improve the standard deviation, but the distribution is not exactly symmetric. And this new phase estimation primitive gives you something which is perfectly symmetric, and that preserves the standard deviation of the outcome distribution. So this is for the case of observables which are projectors. And then for the general case, which is the one that you really need for partition function estimation, you can kind of build up upon this result, and you can kind of obtain reduction to this base case by using some other types of quantum algorithmic techniques. Okay, so let me conclude with a few open questions, which I think may be interesting to look at. So the first very natural question is it the end of this framework for speeding up partition function? The best we could hope for is to completely get rid of this prefactor, which would give a full quadratic quantum speedup. For instance, meaning we could count independent set in linear time. And a nice consequence would be that in many cases, sampling and estimating partition function would have the same complexity. And maybe not, and in that case, can we find a polynomial separation between the estimation task and some counting task, or estimation, separation between estimation and the sampling task for some concrete Hamiltonian. Yes?
Explain where this log is coming from, because I'm confused.
What is
where the log of omega is coming from? Did you explain this, or did I miss this?
so? Or where does it come from? This one?
Yes.
I would say the main reason is because we don't really have a full quadratic speedup for the length of. Okay, so you have this. Let me take the picture. Okay, so you remember you have this picture of like intermediate parameters that you have to interpolate to arrive at the last value. And we don't have a full quadratic speedup for this, for finding those values and the length of those values. So this is maybe the place to look at if you want to remove this log factor.
So the values change in the quantum.
Those
The values of lambda.
you can compute them faster, but not as fast as you would have to do if you want a quadratic speedup.
I would assume that you see lambda subscripts are independent and independent sets. Can you explain how you make that independence? This sort of say interpolation of partition functions, or partition interpolation of partition functions. Can you explain how? We have independent sets, right? And there are partition functions and this independent set. The partition functions are unique independent. Right? Just by inspection of it.
I'm not sure to understand the question.
The Z functions.
Yes, the Z function.
Unique independent.
Unique and independent? What do you mean by?
Z lambda naught, Z lambda naught, right?
Yeah, yes.
And here.
What was the question?
If you explain how they are quite independent, is there some kind of formula and you can about?
How can you express the partition function at each?
How do you see lambda naught different from Z lambda?
Why is it different? Well, it's just because you are evaluating the partition function at different values, right? So it's kind of, yeah. You're evaluating the function at a different temperature. Is it your question?
So isn't that we're getting a quadratic improvement in each of the lambdas, but the number of lambdas is not, it's, your running time depends on one board or the product of that, and is the number of lambdas not increasing either? Is that where you're getting this box for one of the boards? So you're doing this computation of these ratios.
Yeah.
Each of those ratios, you're getting a quadratic improvement on this.
Yeah, for each of them, if you only look at the complexity of estimating the ratio, you do get a speedup.
So now the question is, how many do you have to compute?
Yeah.
And you'd have to reduce that number also by a quadratic factor together.
Yeah.
And you're not reducing.
And you would also have to find this efficiently. Yeah.
And what does it mean to find them?
Find them is like finding those lambdas such as you can guarantee that it does not change too much between two constants.
And where did you do that? How did you?
So I didn't talk about this thing. It is using the convexity of the log partition function. It's very beautiful algorithm. But yeah, I didn't talk about this part. You can do some kind of cover search to find the next right lambda pi. You can do that iteratively.
And then you have some sort of bound on how often this will happen.
Yes,
Which is independent of the algorithm.
That would be independent.
Meaning it's some absolute bound on, so that has to do with how much this varies and so on.
Yeah, it tells you how many IBM values you have
In the worst case.
and it will not be too much, something like square root n for the answer.
Sorry, this is also paper by Grover.
This is essentially, okay, so I go back to the beginning, but this is the last this paper by Harrow and Way, like 2 or 3 years ago, where they propose a way of quantizing this state. But they do have a speed up, but yeah, it still doesn't allow to obtain full.
So that step of calculating the lambdas is also quantized?
It is also quantized, and this is part of how you can obtain this result. Without this step, you would have a worse.
So that number of lambdas is square root of that, and therefore you get.
I think this is the reason. Yeah, the number of lambda is square root of log of omega. So I think this is why we do that.
So calculating this partition function can also be phrased as a tensor network, where all the bonds are on dimension 2, as far as understood. Have you any idea what the tree width would be of that network? Because normally that's how they prove that the Monte Carlo mixing is efficient. Right? So they must have some bounds on the tree widths and all this for this graph. So would that mean that actually there is an efficient way of contracting that tensor network?
Yeah, I'm not an expert on tensor network to give you an answer.
Can you say that again? Can you say?
So this partition function itself is actually a tensor network,
Yeah.
where one dimension 2. And I assume, I guess that the way you prove that there's an efficient mixing for a classical algorithm is that there's like a small tree width, that there's like some flow from one to the other one, and that might suggest that actually if you contract a tensor network that you don't need much Schmidt coefficients to keep track of.
But they're not. In fact, they're not using the same.
No, I know.
But you're
It's a completely different question. It could also be that there is actually an efficient classical algorithm that has nothing to do with Monte Carlo, but that's a network contractions.
It seems that might well be the case for this example.
Yeah, I don't know.
Is the exact counting known to be hard even for these low degree cases?
Yeah, I don't know.
You said this through regular, isn't it? Should be hard.
I mean, if the degree is extremely small, it will be easy at some point. But yeah, I don't know in which regime you can hope for an efficient exact counting. I think usually you don't expect to have an efficient, or you have to move to different kind of assumption, like a precision which is exponentially worse than what we could hope for with efficient algorithm.
Okay.
So you have to make some some other kind of relaxation. Okay, so let me just finish with a second open question, which of course is to try to adapt this framework to quantum partition function. So thanks to the result presented this morning by Anthony, we may now have a way of preparing quantum Gibbs sample using this type of Markov chain method. And so the next question could be, could we kind of use this ability to estimate partition function of quantum Hamiltonian? So I don't really have an answer to this question, but I think there are at least 2 interesting tasks to look at. One would be, how efficiently can you estimate those type of ratio when the Hamiltonian is quantum, given the ability of preparing the quantum Gibbs state? Yes?
translate it to the work of that Amoudi presented, because we're talking now here about the purification quantum example of the.
So yeah, I'm not saying there is a direct implication. Like I'm not saying you can apply it as a black box. I'm just saying you could try to get inspired by the idea of the class of this approach and try to adapt it to the quantum setting.
Okay, but there is a serious issue here in just starting the translation, because here you're talking about the pure.
Yeah, of course, you have like the standard basis for your Hamiltonian, so it's not clear that you can do something efficient. But you can still do some steps of the plan. So for instance, estimating this quantity, I think, can be done with phase estimation. Maybe not with the right accuracy, but you can still hope to do some steps of the plan. You can, okay, if you use Hamiltonian simulation plus phase estimation on the quantum gate state, I think you can get some idea of the eigen.
So the quantum gate state is now defined as a superposition of eigenstates?
Over the energy state of your quantum Hamiltonian.
So it's a superposition of the eigen. I'm not understanding. What is the quantum state? What is the state that you're now looking at?
It is the same as. What do you mean? Like, is it a density matrix or is it?
If it's a pure state, then it would be a superposition over the eigenstates.
Yeah. So okay, you can say it's a density matrix, but I think in their work they can actually obtain some purification of the density matrix. So maybe you can start with this purification. I'm not saying this is easy to do, but I think their framework already has some ideas that can be exploited to do that. And what can you do with this computation of the Coulomb schedule when the Hamiltonian is quantum? It's also not completely clear to me that you can still guarantee that you have all the properties that you want. Do that. Yeah. Thank you.
So just coming back to this question. So you said in your algorithm findings, unless you actually have to work to figure out how you could change by small enough amounts.
I think it is a talk about so I'm asking if the sequence exists or if you can find it efficiently.
Yeah.
I would say both would hold, but I don't have like a intuition about like how to find it. But this is probably an important part of the algorithm if you want to come up with an efficient estimation.
So in the quantum case, it's just to clarify again. The Coulomb schedule depends on both the ratio and the overlap.
I mean, what kind of assumption you want to achieve?
No, like what the properties are that your Coulomb schedule is going to depend on.
Yeah.
In the classical case, it's just the ratios, which you don't want to be too large. And now in the quantum case, you also want to overlap between the quantum.
Yeah, you both want the ratio to concentrate well around, the random variable to concentrate well around this value, and you also want the given state to be very close to control. This is
I'd
needed by
actually
the
mean that you need more steps in the quantum case.
It may be. It may be.
Maybe would overlap subsume
No, I think there is. You cannot make. In general, I think you don't have. It's kind of like opposite requirement. One is an upper bound computation, and the other one is a lower bound. It's an upper bound computation on some quantity. I think it's kind of opposite requirement.
You need a lower bound of the overlap and an upper bound of the ratio.
Yeah. And it kind of comes from two different.
In Morocco and Way's paper, don't they actually need to generate? I mean, don't they? In your case, you don't need to. You're assuming you cannot. Right?
Yeah, but they also have to do the same thing. they have also to not generate. They kind of, they kind of find a way of making the entire procedure non-destructive. So that's the same kind of idea. You can use the deep state, but at the end you have to restore it to its initial state. But it's very important in the framework. If you destroy the deep state, or if you need it, it makes everything worse than classical. So they also assume that you have a warm start and you kind of preserve it without the complications.
Thank you.